Welcome back to the final course in this series on asynchronous programming, where we're going to dive deep into the .NET internals. So far, we've been looking at how tasks work. We've talked about threading, multi-threading, running tasks in parallel, running tasks asynchronously, serially. But in this section, we're going to tie it all together. We're going to look at the actual .NET components that live inside of Thread, that live inside of tasks, that allow us to take advantage of async await in .NET. Now, most of what we're going to talk about, the examples we're going to show in this section, likely you won't ever use practically in your day-to-day job. It's very rare that you'll be creating your own threads, for example. It's very rare that you'll be creating your own synchronization context, for example. But in this section, I want to share with you the underlying components that enable async await for us. Even if we never use them in our day-to-day job, they're very, very important to understand how things work under the hood, because there will be a day where you run into a bug that nobody else can solve, and it's only because we know how async await works under the hood that we'll be able to fix it for our team. Let's jump in. Now let's start out by talking about thread static. Thread static is an attribute that we can add to a static field that essentially keeps that field's value specific to each thread. So even though in this example here, we have an integer that's static, and typically what static means is that there's only one instance of this value. So without thread static, thread local value would remain the same across users, across threads, across classes. But when we assign the thread static attribute to it, it tells .NET to keep this value on the specific thread that assigned it. Now, something to keep in mind are the security concerns that come along with thread static, because .NET does reuse threads. So for example, let's say you have an ASP.NET Core API, you have multiple API requests coming in every second, and eventually a thread will get reused. And we don't want to accidentally leave a user's information on a thread static variable for things like managing the thread pool. So instead of using something like the thread static attribute in your ASP.NET Core API, you would want to leverage something like HTTP context, which is unique to each user request that's coming in to your ASP.NET Core API or your ASP.NET Core website. And one other gotcha with thread static is that tasks may continue on different threads. There's no guarantee that your task remains on the same thread for its lifetime. And if we await a task, for example, and it sets the value of thread static, and then when we come back, we don't return to the calling thread because we've used something like configure await false or configure await options.none, well, now the value we set to our thread static variable is going to be different moving forward, again, causing weird bugs in our code. Let's jump into some code and see an example of how it works. Here, I've created a simple example using a console app where I've created a private static int thread specific value and applied the thread static attribute to demonstrate that this integer will have different values across threads. Now, in this specific example, we're going to set initially thread specific value to 100. We'll print that out showing that our main thread has a thread specific value of 100. But then what we'll do is we'll create two new threads. Now, again, I don't recommend you create your own threads in your code. It's much more efficient to allow .NET to do that for us using tasks and async await. But for this specific example, we need to create our own threads to ensure that we can set the thread specific value on different threads for this very specific example. So again, I don't recommend you creating your own threads in your code, but here is an example where we're going to do it. So the way this works is we'll create two threads manually. We'll start the threads. Each of these threads are going to run this method down here called thread method, where it essentially is going to set the thread specific value to a random number and then also print that to the screen. So in our console, we should see our main thread's thread specific value, and then we'll see two more console.write lines that are running on different threads, background threads, that set the thread specific value to a random number between 1 and 100. When we call thread1.start and thread2.start, well, it starts the threads and allows these to run in the background. .join allows us to wait until the threads finish before we continue. When everything's done running, we'll see this one final console.write line that says that everything's finished, and we'll print out the main thread-specific value one last time. Well, let's run this code and see what happens. Okay, great. So again, we manually, in our code, set thread-specific value to be 100 on the main thread. So as we expect, we see main thread's thread-specific value is a 100. Perfect. And then we spun up two background threads, thread 8 and thread 9, which set this thread-specific value to 5 and 8. And then we returned back after these threads finished running to our main thread, where again, we see that that thread-specific value is still 100. This shows that the thread-specific attribute that we can apply to a static field ensures that that static value is specific to each thread. And that value remains even as we change threads, which we see here at the end, where the value on the main thread was still 100, even though we set the thread-specific value on multiple different threads. I'll see you in the next video where we talk about system.security.principal. Now let's discuss iPrincipal, which is an interface inside of the namespace system.security.principal. iPrincipal is very commonly used in ASP.NET Core applications. It can also be used in desktop applications like WinUI, and in mobile frameworks like .NET MAUI, we default to the native iOS and Android implementations instead. So in this example, we'll focus mostly on ASP.NET Core and how multi-threading affects our principal. You might also hear principal colloquially called the security context, because this is where all of the information about the user, their roles, their claims, what the user's allowed to do, what permissions they have, are all stored here. Now, the principal can be tied to a specific thread, like we see here in this example. However, we probably shouldn't write code like this in our apps, because the good news is, in ASP.NET Core, it's handled for us. Let's jump into some code to see exactly what I'm talking about. Now, what I've created here is just a file new app using the ASP.NET Core MVC template. And I've added a couple extra controllers. So we have our default controller, which we see here in the browser on the right. But what I've added is a login and a log out controller. And if we jump over to that code here inside the account controller class, what we'll see is that we're using the claims identity, the claims principal to sign in our user, in this case, storing the authentication as a cookie. What I want to demonstrate in this example is that ASP.NET Core actually does propagate our iPrincipal across threads, even though it is and used to be thread specific. So let's go ahead and run this app and see how it works. Now, I'll click the debugger and I'll keep my breakpoints here so we can check the code along the way. All right, now here on the right, in my browser, I'm going to navigate to my login controller, which requires me to go to /account/login. Okay, and we hit our first breakpoint. And what I want to show is in a ASP.NET controller, we have access to this user variable. And this user is where we can also get all of the claims, the identities stored for this user, which is a claims principal type that implements iPrincipal. Now, the other information that's important to us in our ASP.NET Core apps is our HTTP context, which is specific to each HTTP request. So it's the user object and the HTTP context object that allow us to pass user-specific information around. And in ASP.NET, before .NET Core, so the original ASP.NET, not ASP.NET Core, what would happen is if we switched threads, we would lose this information. Now, here, we're in an ASP.NET Core app running .NET 9. This is all modern. Now, what I want to show you is I've added here a configure await option, or a couple configure await options, to our sign in async method, where I'm going to say force yielding, meaning we're going to force the .NET runtime to move us to a background thread to run this code, or rather, we're going to force the .NET runtime to yield the current thread to run this method, even if it's already completed, even if it doesn't need it. And I said configure_await_options.none chained together with force yielding so that the next line of code will resume on a different thread. Now, if we first look at our user object, we can see our information about the user. The user type is claims principal, which inherits from iPrincipal, which is how we were able to retrieve all of the claims and identities for me, the user, who's not yet logged in. And likewise, this HTTP context contains all the information about the incoming request. And it's, again, very specific to me, this user who made the request, and should never be shared with other users. Now, before I tell this code to continue executing, I want to highlight that we're currently on thread 30. And because I've set the configure await options to force yielding and none, we should yield to a background thread to run sign in async, and we should continue running on a different thread for the next line of code where we return back to the index. So let's go ahead and resume the program. And there we go. Now we see we're on thread 37. And if we look at the HTTP context, thread 37, even though we're not on our original thread anymore, this still has the same information that you can compare. If you just jump back a couple of screens in the video, you'll see the same information here in HTTP context that we saw earlier. The HTTP context and our iPrincipal, our user, is passed along. And we can also see that our user is now authenticated, and we have the two claims that we created manually here. Now, I should also caveat this with, these claims are hard-coded. This is not how we should do it in a real-world app. But to demonstrate it for you here in a simple app, it's okay because I'm never publishing this to the internet. Please don't do this in your app. Now, the way this works is thanks to something called the execution context. We'll jump into that in the next slide. Execution context for our ASP.NET Core apps essentially saves the HTTP context and saves the user information and brings that along as we jump between threads. Now, one important thing to keep in mind is that if you're working on an older app that uses .NET Framework before .NET Framework 4.5, then this could be a problem for you. Before .NET Framework 4.5, which, by the way, if you've never heard of .NET Framework, that's okay. .NET Framework 4.5 actually came out in 2012, so we're a good decade past its release, and I hope not many folks are still forced to work on pre-.NET Framework 4.5 apps, but if you are, the HTTP context and also the iPrincipal did not come along with us when we switched threads. So if we had this code in our .NET Framework app, which technically the configure await options were introduced in .NET 8, which came out in 2023, so this exact code wouldn't even run. But if we do ever find ourselves where we're switching threads, where we're using async await, and we do not return to the calling thread, in .NET Framework before 4.5, we would lose our HTTP context and our user. Now, the good news is this has since been fixed. So since 2012, .NET Framework 4.5 and all of the .NET cores don't have this problem. But I did want to share this with you earlier because thread.currentPrincipal is real. We can assign the current principal of a thread, but we shouldn't do that. We should let .NET take care of that for us. And as we'll see in the next section, execution context allows information to be shared across threads and to continue on instead of in the old case of pre.NET Framework 4.5, where it would lose this information. Now let's go learn more about execution context.